All right, so what I'm going to do, we're going to go through some questions. Right, I'm going to flash up a typical question, question 1 or whatever, on the board. Okay, I'm going to give you guys kind of 5-7 minutes to try and answer it. Okay, go through your class notes, find the section that's actually relevant, know the answer. I'm going to then physically ask you guys, hey, what's the answer? Yeah, and then if you get it right, good, we'll move on. If not, we'll flash the answers up so you can have a little bit of a look. Right, at what you should be writing or how to approach a particular question. All right, so let's have a look. So this is a typical question 1. Question 1 is usually easy. Short, single word or 2 or 3 word answers or examples, okay, only worth a few marks each. Okay, that's our settler. Settler question, everybody gets in there, has a look, settles down, starts the exam. Okay, so I'll give you 5 or 7 minutes, maybe 10, there's a couple in here. All right, see if you can find some of those examples, find some examples that fit those answers from your class notes. Okay, how did you go? Did we get some answers out? Did you find some of those earlier examples? Probably pulling those from lecture 1, I'd say. Okay, so has everybody at least had a chance to have a think about each of those now? Yeah? Let's have a look. Okay, so question 1. A. Give 4 examples of factors or variables that might affect, alter, or influence reaction rate kinetics. Pretty easy one, huh? What are some variables that might affect reaction rate kinetics? Yeah? Temperature? Yeah. It's probably the most obvious one. What's a couple of others? Pressure? Yep. So thermodynamics. Yes, enzymes or catalysts? Yep, definitely. Or inoculants, sorry. A concentration gradient? Yep, pushing a reaction in a certain direction at a different rate. Can anyone think of another one? Yes, so agitation or stirring, shaking, something like that. Yeah? Temperature, catalysts and enzymes, inoculants, substrates, diffusion, also an important one. Okay, thermodynamics or driving force. Okay, so any of those, or if you can think of any specific ones, that's also okay. All right. So if that one's asking for 4 examples, they're essentially worth half a mark each, and they are. They're going to be essentially a 1-word answer or multi-word answer, just like these. Okay, so that's what we'd expect for that sort of question. All right. So moving on to 1B. 2 examples of diffusion in gases. What's some examples of diffusion in gases? We're just talking everyday examples. Yeah, so perfume, sure, but let's be a little bit more specific, okay, and try and answer the question. All right, so saying perfume, what's perfume? Perfume's a liquid in a bottle. All right, what are we talking about when we're talking about the fusion of gases in gases? Yeah, so it's the vapor or the smell of perfume crossing from one point to another point, or moving from one point to another point, yeah? So we can't just say perfume or exhaust fumes or something like that, okay? Let's be a little bit specific in the exam paper rather than just a 1-worder. All right. So, yep, top answer, diffusion of perfume or odour from one side of the room to another. Cigarette smoke escaping from smoking lounge in airports or pubs, okay? And there's usually a visual indicator associated with that. If you've ever been through any, the best example I can think of is European airports. Okay? In most European airports, particularly in Middle Europe, Germany, Switzerland, they have the Camel smoking lounges at the airports, sponsored by Camel, cigarette manufacturer. In those rooms, you can't see the people within them because it's just that heavy with smoke, and when they open the door, it's just this waft of smoke comes out. It's pretty disgusting. But anyway. Another one, steam from a kettle. Okay, so again, there's a little bit of a visual indicator, but basically steam, vapor form of water, humidifying a room, for example. Okay, so they're the types of examples that we'd be looking at there. So be a little bit specific in how that applies to diffusion. Don't just say perfume or smoke. Okay, so 2 examples of diffusion in liquids. What did we come up with? Osmosis. Is that an example or is that a mechanism? Yep, okay. That's very mechanistic. Is there any other specific examples people can think of? Yeah? Yep, so coloured dye, okay. So we've got a colour indication of diffusion of a liquid within a liquid. Yeah, so they're the types of examples, okay. The ones that I have here, tea dissipating from a tea bag in hot water. So we've got a visual indicator, okay. We can see dissolved compounds, okay, flavour, colour, dispersing through our tea. until it's uniform, yeah? Fresh water entering the sea at the mouth of a river. Okay, so often we might see it on the Nature Channel or something like that. Amazon's a couple of examples where we get fresh water or muddy water or something like this entering another stream. They mix, diffuse into a single stream. Okay, where we can get variations in concentration of things like salt, salinity, or sediment. Yeah, food colouring, dye in water, obvious ones. Okay, what about D? Did we come up with any examples of diffusion in solids? Yeah, carburization is an example. Okay, well, we have carbon coming from the atmosphere, adding, absorbing to the surface of our, typically a steel, okay, and diffusing into it. Yeah, nitrogen does a similar thing. Any other examples?
Semiconductor doping.
Yeah, yep, for sure. Okay, so carbon diffusing into iron during carburization. Formation of a binary compound in a two-element diffusion couple. So hopefully Rakesh looked a little bit at those diffusion couples. Okay, element A, element B, put them together, heat them up, diffusion across the interface. Precipitation of an intermetallic compound during heat treatment of an alloy. Yeah, so atoms have to diffuse, localize, get the right stoichiometry, and then we can start to grow precipitants within our alloys. And again, the answer we already received, semiconductor device doping. Okay, where we have either a thin film or heating within a certain atmosphere where we can get certain elements to go into our semiconductor to improve its performance. Okay, so this one, we've lost our spark, but what process, what is nucleation, and what process typically follows the generation of a stable nucleated embryo of a new phase? So this is essentially a description, okay, taken straight from our slides. Nucleation is the first step in the formation of a new thermodynamic phase or structure. Okay, if you can get that one, that's a pretty good start. Okay, again, it's worth 2 marks here, so we're expecting a little bit more from you. All right. Nucleation is defined to be the process that determines how long we wait before a new phase appears. And once we do form our stable embryo, okay, nucleation is then followed by growth. Okay, so learn those definitions because they will pop up. Okay, so everybody got that? Yeah? Okay. Question 2. Okay, so how did we go with this lot? Has everyone had a chance now to at least have a think about each of those? Got a rough idea what the answers are? Yeah? Okay, so a couple of examples for question 2A. So 4 everyday examples of nucleation and growth. What did we come up with? Condensation? Yeah, it's typically from that set of lecture notes. What's a couple of others? Cavitation, yeah? Yep. Yep. Okay, so typical examples, evaporation and vaporization, condensation, melting is another one. Crystallization, of course, precipitation and recrystallization, okay, a little bit more complex, and effervescence, okay, which is a less technical term for vaporization out of a supersaturated solid solution. Okay, so that's all we're after there. Some very, very simple examples. Okay, so 2B, did we find our definition for homogeneous nucleation? Yep, would have been there on one of the key slides at the start of lecture 2 or 3 it was. All right, so we have to be able to distinguish between the two, obviously, for an exam, okay, and for your learning as you move forward, all right. There's some key words in here that if you're having trouble figuring out what is homogeneous, what is heterogeneous, okay, but for an answer worth 2 marks, you're really going to have to get some of these key words into your answer. So occurring randomly or stochastically within the body, all right. Describing how it happens, fluctuations of the nucleating phase appear in decay, okay, until a large fluctuation that's large enough to overcome the nucleation energy barrier, okay, where it's more favourable to grow rather than decay. Okay, so try and get a little bit of that mechanism in there if you can. Okay. But if you can remember at least this first line, randomly within the body, okay, without external influence, that's key. Same for heterogeneous, we all know the difference hopefully. Okay. So heterogeneous is when nucleation occurs in proximity to a foreign body or defect. Alright, so foreign body or defect, this is what's starting it off. Sensitive to impurities, in contact with the system. And the next key set of words here is they create a lower energy site or interface for nucleation to occur. Right, so they're the things that distinguish the two. Okay. So a little bit of why heterogeneous nucleation occurs, a lower energy site. Okay, so D, traditionally we try to have the Mentos-Diet-Coke reaction in our slides and in our exam. Okay, so what is the driving mechanism for the Mentos-Diet-Coke reaction? We all know what it is? So it's nucleation driven, where the supersaturated dissolved CO2 in the carbonated liquid can be rapidly nucleated at the rough and porous surface of a chemically compatible Mentos candy. Yeah? So for starters, the Mentos is chemically compatible with the Coca-Cola or the CO2 that's trying to come out of the Coca-Cola, the Diet Coke. Okay, if it wasn't chemically compatible, it wouldn't be able to nucleate or inoculate from that site. And then we've got geometric features here that assist in local nucleation. Another one, which is probably going to glean you the last half mark out of this question, is why Diet Coke as opposed to any other carbonated drink. Diet Coke has other chemicals in it as well, Do we remember what it was from our movie in class? What's Diet Coke got in it that regular Coke doesn't? It's got artificial sweeteners, yeah. So aspartame is the one in there that acts as a catalyst to the nucleation as well. So that's why Diet Coke goes better than normal Coke or Fanta or anything else. Okay? So there's a catalyst in there, aspartame, which helps the forward reaction. Okay. Right, we remember our other movie with the beer glasses, okay, or the champagne flutes, for example. So what physical aspects of the glass or cup could contribute to enhanced effervescence, or the rate of CO2 vaporization from a carbonated beverage? So geometric aspects of the container. Okay, so for a champagne flute, a very sharp conical point will act as a nucleation site for those gases to vaporize out of solution, supersaturated solution. Okay. They provide essentially a high local surface area or point of lower pressure for this to occur. Deliberate surface etching or scribing a pattern on the surface of the glass. Okay, so we saw laser etching and things going on with those beer glasses. Okay, again, creating a heterogeneous nucleation site of lower energy for effervescence to occur. Or the other one, a dirty glass, okay, where a localized surface impurity could trigger CO2 nucleation. All right, so if you've got a residue or dirt or something attached to the surface, the inner surface of the glass, this too could act as a heterogeneous nucleation site. Okay, so think about the bartender polishing up the glasses. The reason is try to get them as clean as possible. Okay, everyone clear on that? Okay, so the first two, fairly simple. All right. Question 3 is where things get a little bit harder and we start to bring in some of our theory. Have you found the slide for this one? I'll just see if we jump to B or whether we have the answer here. Yeah. Okay. So what's delta T commonly referred to as with respect to solidification? Undercooling. Yeah, delta T is undercooling. Don't forget to name that if that one pops up in the exam. Basically with these exam questions, if you see a comment from me in brackets, like a schematic graph of the free energy G of the liquid and G of the solid may assist here, you'd probably want to draw it, okay? So anything in brackets is usually a hint or a tip or a clue as to how they answer the question if you get lost. All right. Okay, so hopefully we got delta T is our undercooling. All right. Now you have to be able to either draw this figure here, which I strongly recommend you understand and learn, okay, and at least be able to see or show, okay, you've got a formula there in the question to help you. Okay. What you need to be able to say is that delta T, an increase in delta T, increases the driving force for solidification. Showing it on a plot like this is the most awesome way to do it, and if you get that plot right, I'm going to say, well, there's 2 out of 3 there. You can draw something that looks like the process. Okay. Knowing what delta T is a very good start. That'll get you a half a mark. Right. But explaining how the two are related. Okay. So our energy curve of our liquid, energy curve of our solid, intersection point, delta T, directly proportional to our delta G. Okay, so there are our key takeaways for that question. And that one was worth 3 marks. All right, so I'd strongly recommend that you go over our classic nucleation theory slides. Okay. All right, so that was 3A. This is 3B, and again, it's all about classic nucleation theory. Okay, so did everybody find the right slide for this one? How to answer it? Okay, again in the brackets, clue, breaking down the equation into its two components may help. Something you've also got to keep an eye out, and this is where some students fell short last year. The question is specifically asking for a schematic graph here. Okay, sometimes students will get a little bit flustered in the exam and not read that part of the question. Okay, so using the graph here is essential. All right. You can do your best with words, but it is asking for a graph. All right, so let's have a look here. So hopefully you found this slide here. Yep. So how the free energy of the system is changing and how we get to a point where a stable nucleus can begin to grow. All right. So breaking it down into our two parts of our equation. All right. Both of them are associated with different types of energy. Okay. But the first one here, which is negative, right, has to do with our volume. Right, the volume of our nucleating embryo. Right. The second one here has to do with the surface area. Okay. And you can see here, this is the graph that I'd be hoping you could reproduce and understand. Okay, our delta G, positive, negative, over R, the radius of our embryo. So we've assumed in the question there a spherical embryo. Okay. So our surface area component, which deals with the resistance to the nucleation of our solid particle based on surface tension, is this curve here, which represents this section here of our equation. And this one here, which is negative, of course, has to do with our volume. Right. So hopefully you can label this correctly, see that the cumulative effect results in, firstly, an increase in energy and then a decrease in energy once we get to a critical radius value. Yeah. But also, hopefully you can explain to me that this all has to do with geometry, in that it's a competition between the volume, and you can pull out the relationship between a sphere, the volume of the sphere, and the surface area of the sphere here. Okay? So when R is small, surface area will dominate. As R increases, the volume will dominate. Right? Once we get past our critical R star value. Okay? Are there any questions on that one? No? Okay, so again, I recommend that you go over the classic nucleation theory. Okay? But understanding these concepts here, okay, you're probably going to be able to get some very good marks in question 3. All right, we'll move on to question 3C. The answer's already up there. Okay, I'll go through that and then we'll have a little bit of a break. All right. So this one here leads on again from the previous question. Okay. This one here is specifically asking for the relationship in terms of radius and spherical geometry alone. Okay. So we've kind of half answered that already in the last slide. Okay, so it simply comes down to the rate at which the volume of the sphere increases compared to the surface area of the sphere as radius increases. All right. So this one's a good one to know. So when R is greater than R star, 4 on 3 pi r cubed is greater than 4 pi r squared. Hence delta G continues to decrease from that point. So again, being able to understand this figure here is key to getting your marks out of this section. this is annoying. I'll just go through this one with you since the answer is not going to disappear. So question 3D, and this is typically where we'd complete question 3 on classic nucleation theory. So according to classic nucleation, the equation for the change in free energy, delta G, with respect to the nucleation of a solid, let's call it beta, from another solid phase, alpha, includes an extra term compared to equation 2. What does this third term represent and why is it important? Okay, so the previous equation, equation 2, didn't have this one here, yeah? Okay, because it was just the nucleation of a solid from a liquid. When we are nucleating a solid from a solid, we get this extra term here in our equation. Okay. This third term represents the misfit strain energy. Okay, so that's the key word, misfit strain energy. Nucleating a solid from a solid, we have this extra energy associated, okay, because essentially that parent phase, that alpha phase, is not flexible like a liquid. Okay, it's stiff, it's solid, it's creating further resistance for nucleation. Okay, so it's essentially the energy penalty of the solid host lattice accommodating the new solid phase. Okay. And usually this has to do with large differences in crystal lattice and structure. Right. And I've got here in brackets, doesn't exist in the liquid case because the liquid can flow around the new phase easily. It's not restricted. And you can see it's also a positive contribution. Right? So it's telling us straight away that it is much harder or significantly harder to nucleate and grow a solid within a solid compared to a solid from a liquid phase. Right. Let's see what the next slide is here. So everybody kind of grasped that concept. We have that extra term there, making things harder, solid from solid. Now, even though it's not asking, sometimes it's good to throw in a figure. Okay, so this figure here is essentially very similar to what we've just drawn for question 3B and C. Okay, but with our extra term, all right, our misfit energy. Okay, we move from here. This is the case if it's with the liquid. Okay, but with the solid, we've made it a little bit more positive. Right, so you could even demonstrate that. That would impress the marker greatly and will probably give you full marks. Okay, so with that extra term, we go from this one here for our volume, purely volume energy association. We add something that's a little bit more positive and shift it up to here. Okay, and that shifts this curve compared to what it would be for the liquid case. All right, so we'll pull it up there and have a break. I'll just leave that slide up. If you've got any questions, come on up. We'll take about 5 minutes. 7 minutes or so for a little bit of a break and a reset. So I'll pop up question 4 anyway. We'll just give you a little bit of extra time. So if you wanted to do the survey now, that's fine. You'll have a bit of time to do it. But I'll pop up question 4 in the meantime. Okay, so how did you go with question 4? Okay, so they're getting a little bit trickier now and more specific. Okay, but hopefully you've found the slides and things in the class notes to help you along. Okay, so again, question 4a. Okay, this one's very, very specific, very, very high marks here, and drawing the diagram here is probably an essential. All right. So it refers to this particular slide, okay, and we want to name these 7 stages, okay, for crystal growth in the slow growth or spiral growth regime. Okay, so hopefully you can actually understand or remember, okay, these 7 steps, not including 4-star. All right. Okay. So I won't go through them in detail. It's pretty self-explanatory once you've got the slide there in front of you as to what's going on. But hopefully this mechanism makes sense to you. Right. Often students in past exams have forgotten the boundary layer. Okay, diffusion through the boundary layer. That's one that's commonly forgotten. But yeah, try and think about it as a process at which we can minimise the entire structural energy of the attachment of that molecule or atom. Okay, so moving from where it's free in the liquid through a boundary layer, attaching to the surface. Remember, we've only kind of got a couple of bonds on the bottom there attaching it. Moving it to an edge, reduces energy, we've got more bonds attached, and then moving to a kink or step or vacancy, we can reduce the structural energy further. Okay? But yeah, strongly recommend being able to draw that diagram. All right. Question 4b. What are the other 2 typical types of crystal growth as growth rate and surface roughness are increased? Okay. We have birth and spread, where we have multinucleation and multi-layer growth occurring. Okay, so this is a faster growth rate. Okay, it's not our attach, move, minimize energy over a long period of time. And then we have adhesive growth. Okay, so this is non-sequential, rapid surface addition resulting in dendrite and other non-flat structures that we see. All right. Okay, so again, this one's only worth 1 mark, so basically it's a 1-word answer, half a mark each for those 2 different regimes. All right. Hopefully you remember what a TT diagram is. Okay, what does TT stand for? Okay, time temperature transformation diagram. Okay, quote that. If it comes up, label it. Tell me what it actually is. Okay, don't just say TTT. What are these diagrams typically used for? Okay, and we had several examples in class, some from the liquid to solid transition or liquid to crystal transition, and some utilising the steel TTT diagram, where we saw phase transformations. Okay, so in practice, nucleation and growth of one phase from another is presented by time and temperature on the transformation diagram. Okay. So these are measured or calculated diagrams to assist in predicting the time and temperature windows for the evolution of specific phases. Okay, so that's the key sentence you want to be able to remember. What is a TT diagram used for? That's it. Obviously very, very useful in industry when we're trying to tailor the properties of our material by its microstructure. Okay, so cooling rates in things like steels, highly hardenable steels. Okay, the microstructure is very sensitive to cooling rate. We want to know where we are because the properties can vary greatly. Okay, so there's 2 examples there, the ones that we used in class. All right. Remember, we had our cooling rate curves. Okay, so we're usually starting in one phase field, moving into another phase field, or trying to avoid a phase field. Yeah? Does everybody understand those diagrams and what they're used for? Okay, so these are often ones that I'll get questions about, usually a few hours before the exam. Okay. All right, so what aspects of a molten alloy, thermodynamic, structural, physical, or chemical, assist in slowing crystal nucleation and growth kinetics, leading to the possible retention of the liquid amorphous structure upon rapid cooling? So this is metallic glass stuff. All right. So packing efficiency, remember, closer those atoms are together, the lower the structural energy of the liquid state. Okay, and if we have the structural energy of the liquid state very close to the structural energy of the solid state, then think about our classic nucleation theory. The size of that delta G, the difference between the solid and liquid lines, is very, very small. Thus, we can undercool a long, long way without increasing the driving force for nucleation and growth too much. Right? Once we get to a very low temperature, the system freezes. Diffusion is no longer possible, particularly below the glass transition temperature. Okay. Packing efficiencies are also associated with slower kinetics, slower diffusion rates in general. If those atoms are all packed in space very efficiently, all in contact with one another in the liquid state, it's very, very difficult for them to try to rearrange and form crystals. Okay. Essentially, the viscosity of the liquid will also increase. That's something we observe. So when we hinder diffusion kinetics, we hinder nucleation and crystal growth kinetics. If atoms can't rearrange themselves to form a nucleus, then crystallization and growth is slowed down dramatically. Okay, the other thing that we look at, okay, those low melting points. So liquidous lines or deep eutectics. Okay. This tells us that the thermodynamic driving force for crystallization is lower in that region. Okay, so remember, it's a thermodynamic competition between the liquid and the competing crystal phases at lower temperature. Okay. All right. Last question. Okay. Question 5. Okay, so how do we go with question 5? Yeah, has everyone had a chance to find everything they need to answer those? Okay, well let's have a look. 5A. Okay, so in terms of activation energy, Q, generally speaking, how does the activation energy for diffusion of an impurity element over a surface, usually denoted by QS, compared to that of the grain boundary, QGB, or solid lattice, QL? Okay. So the activation energy Q for the lattice is much higher than that of the grain boundary, which is again higher than that of the surface. Okay. So remember that order. Okay. If you're having trouble remembering it, just try and visualize what's going on there. Okay. So again, at the surface, if you've got an impurity atom diffusing across the surface, how many bonds is it making with the surface? Not a great deal. It's just what's in contact with the surface. Yeah. In the grain boundary, what's our grain boundary? It's a highly disordered structure. There's gaps and holes everywhere. Okay, so again, fewer bonds compared to the bulk, okay, where it will be bound in every direction in a very solid way. Okay, so think about it in that sense. A next level answer, if you can actually remember these ratios here, okay, it's also important or useful. All right. Click that up there for a second if you need it. All right, so that's the key takeaways for activation energy. We can think about it in terms of bonds. B, something that's highly related, how does the diffusion coefficient of an impurity element over the surface, ds, compare to diffusion in a grain boundary or in the solid lattice? Okay. Second part of the question is also a little bit of a clue. How is this related to temperature and activation energy? So hopefully a good student will think about some of the relationships they've learnt during the course and pull out Fick's second law. Yeah? Okay, so it's reverse relationship to activation energy. Okay? So diffusion via surface is relatively fast compared to a grain boundary or the bulk. All right, so ds greater than dGB greater than dL. All right, then bring in Fick's law. Okay? As the energy required to activate diffusion decreases, the diffusion rate increases. As temperature increases, diffusion rate increases. Okay? So if you can quote that as well as the second part of your answer, you'll get full marks. And again, if this isn't the type of question that you've got in the exam, you've always got this relationship where you can compare D to Q. If you ever forget the way that this works. All right? Okay. Does everybody understand that? Okay. Now, 5C. Other than temperature and activation energy, name 2 physical or geometric factors that may influence grain boundary diffusion rates or impurity concentration over time. All right, so hopefully we recall from our grain boundary diffusion lectures, the key thing that controls diffusion flux down our grain boundary itself, which is physical or geometry factor, is the width of our grain boundary, delta. Okay? So grain boundary width. Something else that can affect it, which is microstructural as well as geometric, is the grain orientation at the boundary. Okay, so remember, the orientation of our grains at the grain boundary affect the characteristics of that grain boundary. Okay. So here the example was a large angle mismatch of the grains, lattice angle mismatch, okay, leading to high diffusivity. Whereas as that misorientation or angle mismatch becomes less, okay, we get less diffusion through the grain boundary. And this relates to how well the atoms can bond across that grain boundary, how much space there is for other atoms to diffuse around them. So another one that you could have also used was the surface layer conditions or initial concentration of the elements that are diffusing. Okay, So again, a higher concentration can lead to a higher diffusion rate. Okay, so that's something physical, a physical part of the system that can limit diffusion. Okay, 5D, pretty similar in nature. So other than temperature and activation energy, name two microstructural properties or features associated with grains or grain boundaries that may influence the overall concentration, for example, carbon at the surface skin of iron during carburization. Okay. So one is just the grain size of the material. Okay. Grain size basically dictates how many grain boundaries or the volume fraction of the bulk material that are grain boundaries. Okay? So a higher volume fraction of grain boundaries equals high diffusion. Grain boundaries are diffusion superhighways, remember. Okay, so a very fine grain size is going to allow for high diffusion rates into the bulk via the grain boundaries. Another one is the grain orientation or isotropy. Okay, whether we've got parallel grains, okay, some form of grain texture in the material. So remember the other week we put up the piece of rolled material, we could see all the grains are in a certain direction. Therefore, majority of the grain boundaries are also lying in a certain direction. Okay, so again, the grain orientation can affect things, diffusion rates, particularly if it's coming from a surface. And again, the spacing of those grain boundaries can affect how rapidly we might diffuse into a material or how it affects the depth of diffusion of an element. Okay, you might have a very, very fine grain spacing, even if it's in just one direction. That's going to affect what our surface diffusion profiles look like. Okay. Slide. So I've got question 6 here. This was added when we did add the segregation section to the course and homogenization. Okay, so we'll take a couple minutes, take a look at question 6, and we'll go through that, and then we're done for the day. So again, these are just examples. There's only 5 questions in the actual exam. Okay, so these are the most recent slides, recent class we've gone through. So hopefully they're pretty fresh in your mind still. First thing to note here, just have a look at the weightings here. We've got 3 marks and 4 marks. Okay, so we're expecting a pretty decent answer for these ones, yeah? Okay, so answering this question with 1 or 2 words is probably not quite acceptable. You're not going to get 4 marks there. But what have we got? Question 6a. What are 2 factors that contribute to elemental segregation in the casting process? Describe the reasons for segregation to occur in each case using diagrams where necessary. So one of the examples that we did show in class, in a perfect solid solution alloy such as copper-nickel binary system, the bonding strength or preferential bonding between constituents, which is often related to their melting point, okay, so nickel up here, can lead to casting segregation. Okay, so our nickel-nickel bonds a little bit more favoured as we're reducing temperature than copper-copper or copper-nickel. Okay, so hence we end up with a segregated structure, right? Where at the core of our dendrite, these preferred bonds are forming first at higher temperatures during the solidification process, and as we continue to solidify at our boundaries, we have segregated to something that's more copper-rich. Okay, so this has got to do with preferred bonding situation, okay, where certain elements want to bond with each other. Okay, and if you can draw these diagrams or something that symbolises this, that's going to help your case greatly if you can't describe it. Okay. So the next one that leads to segregation in a casting is complete liquid-liquid or solid-liquid immiscibility, leading to casting segregation. Okay, so again, a nice phase diagram to show this would be very useful or handy. Right. But basically this concept, again, comes down to bonding, but instead of a preferred bonding between the 2 constituents, it's a repulsion between bonds, okay, wanting them to separate. Okay, so what we end up with as we're cooling, okay, for example, in our brasses or our just copper system, okay, we end up with just pure copper or pure brass dendrites, right, all the way down to the melting point of, for example, lead. Okay, so the very, very last point to solidify here is going to be pure lead over here. Okay, and then they're both solid, and we've got this segregated microstructure. Lead is not in solution; it's out there on its own in pure lead particles. All right. So they're the 2 cases that we're after in that question. Okay, everyone got that? Okay, so 6b, again, we've got a bit of a definition that we're asking for. With respect to a solid solution, what is homogenization? So homogenization is the even distribution or redistribution, okay, so 2 there, even distribution or redistribution of solute atoms from the cast state or prior heat-treated state within a single bolt. Second part of the question, under what conditions can homogenization generally be achieved? Okay. So structural homogenization of the solid solution can be achieved at elevated temperatures. Okay. So most important, elevated temperatures. Okay, we have to be higher than the activation energy for diffusion to occur, okay, to homogenize the system. The atoms can't move, it's not going to homogenize. Okay. A lot of people in their answers will quote 0.9 times the melting point in Kelvin, which is a good start. We also have to be within the solvus boundary. Okay, so if we remember our phase diagrams, we have to be within the solid solution region on our phase diagram, a single phase field. If we're in a dual phase field, we're going to produce 2 phases at that temperature. Okay, so we have to be within the bounds of our solvus boundaries, within a single solid solution phase field. And again, it's good if you can remember some of these phase diagrams. Okay, so that aluminium magnesium diagram is a good one. Okay, and you can indicate that we want to be in our single phase field for heat treatment. All right, so there's two key points there. Temperature within the solvus boundaries or single phase field. Okay, but then the most important one that you've really got to mention is sufficient time. Okay, homogenization is a diffusion process. Diffusion kinetics are involved. Whenever we say the word kinetics, we have to remember time. So a certain amount of time is required for a solute and solvent atoms to diffuse, the required distance for homogenization. And if you want to, you can make some comments here that the grain size or dendrite arm spacings and things can affect that. Slower cooling rate of the casting means we've got greater segregation, means it's going to take a greater diffusion distance to homogenize and a greater amount of time. Again, if you can draw some phase diagrams. Okay, so here's our examples. So in the copper-nickel system, if we had our 50-50 alloy that was segregated like we saw in our microstructure image, okay, we want to be able to increase to a temperature here, which is below our solidus line. So we're in solid state, okay, but we're very, very close to it. We don't want to melt our structure. We want it to remain solid, but we need enough temperature to allow diffusion. Okay, diffusion's enhanced at higher temperature, so as close to that line as we can kind of get safely, we're going to get enhanced diffusion kinetics and homogenize. Here's our example of our aluminium magnesium system. Okay, to homogenize this, depending on the composition of our alloy, we have to raise our temperature out of usually a dual phase field, okay, between this intermetallic and the solid solution, to a point where we're within the solvus bounds. There's our solvus bounds there, and within the single phase field. Okay. We also know at this temperature here that our solubility is going to be highest in this axis here. Okay, guys. I'll hang around obviously for 10 minutes if there's any questions. Okay, but other than that, I'll block out time for our lecture times for the next Monday, Thursday lecture sets. Okay, so if you need to come and see me, send me an email and we'll book a time within those lecture sets or any other time that I've got. All right. Other than that, just drop me an email and I can try to answer any questions as best I can. All right. For currently, again, we haven't had any updates, but the exam will be held on the 4th, from what I can see from the draft exam timetable. Okay. Hasn't been released yet, but that's what it's looking like. All right. Okay. Good luck. And again, any questions, just fire them off.
Take a picture of the answers for question 5, number 4?
Yeah, but it's all on lecture recording as well.
Oh, yeah.
I'll put these up. What is it? For
Question 5, number 4.
sorry?
Question
4.
Question 5.
5. Okay. 5A.
D.
D.
Yeah.
Just wrote that one. Thank you. Okay. So you'll have the lecture recordings, yeah, and I can put that file up a little bit closer to exam time, yeah. Okay. Yep.
Is there lectures for the remaining of the week? No.
Nope. No. So like I said, you got time or any questions? You can book a time to come and see me in the office. But
Mhm.
other than that, no.
All right. Yeah.
That's it for the course. Like I said, this section here is a bit stretched out, and the other two are a bit pushed up.
Yeah.
Yeah.
All right. Yeah. Thank you.
Okay.